So here's the warm-up question. So you should have this in front of you. It's there's a stack of them in the middle of the desk, so make sure you grab one of those. And I got two questions for you. And both questions are related to these two energy diagrams. Now there's a decent amount of details in this energy diagram. I don't expect you to know all these details, but these two questions, theoretically, you should be able to answer those based on what we did last class. First one is, looking at both of these graphs, what kind of reaction are they? Endothermic or exothermic? Victor? Which one? Left one's exothermic. Yep. And how'd you know that?
Because after the reactants, the product.
Yeah, the products end at a lower energy level than the reactants started off with. Okay. So then what would B be? Endothermic or exothermic?
It would be
Also exothermic, yeah. If you were thinking I would do one of those things where I give you one of each, you're wrong. They're both exothermic. Now, looking at them, they look differently, right? The products, you still end at a lower products on graph B. Now, the difference between the two graphs is related to question 2. The difference between them is the size of the delta H. That triangle symbol that stands for delta, what that means is delta, the triangle means final minus initial. So your final value minus your initial value. And H is referring to your enthalpy. So the change in enthalpy is going to be higher. So the answer to that one would be, this question would be A. A is going to have the higher enthalpy because if you look at the change in enthalpy, it is the difference between the reactants and products. It's clearly higher for graph A. Excuse me. So that's really what I want you to be able to do at this point. The rest of today, the rest of these notes is just basically breaking down the rest of this graph and then trying to see what's some of the pieces of information we can get from these energy diagrams. So let's go ahead and do that. So if you got your notes out, go ahead and turn to the energy diagram part of them. And we need to think about a successful chemical reaction. Like we've predicted chemical reactions and then predicting the products and stuff and all that, but we haven't really talked as much about like literally what is happening in a chemical reaction. Last class we did talk about like two things you need for a chemical reaction. You first need to break the bonds that are in the reactants, and then you need to form the bonds that are in the products. And I want to go into a little more detail on that. And this is called go ahead and add this to your notes. This is called collision theory. So collision theory, it is the details, these 3 steps here for how a chemical reaction happens. How you take reactants, and you make products. So here would be the story. Here would be my 2 reactants. So these are reactants here. We have 2 nitrogen dioxide molecules. And my goal is I want to make the product dinitrogen tetraoxide. Okay? Now, in order to make that product, I need to collide. So step 1, first you must collide the molecules together. And I think it's interesting that's like chemistry is literally that simple. Like it's literally just running things into each other and seeing what happens. That's all a chemical reaction is. If things can't run into each other, they can't react. So they first must run into each other. Now, a second thing is, it's not just like any old running into will do. Like if you're trying to get like, if I'm trying to make this cap go on this marker, I can't just like, it's not enough for like the cap and the marker to just collide with each other. They need to collide in the right orientation. Orientation is referring to like how they're positioned. So like this would not be the right orientation. They're colliding, but it's not the right orientation. But if they collide like this, now that's the correct orientation. So then the third thing is they must happen with enough energy. Because you can imagine a scenario where, all right, this cap and this marker, they are going to collide. The orientation of the cap and the marker is correct, but that cap is not on the marker, right? It's still going to fall off because I didn't do it with enough energy. I didn't collide this cap with this marker with enough energy. In a similar way, if you're going to try to bring these molecules together to react, they got to have the correct orientation. So the two ends need to be lined up and the two O's together lined up like that in order to form that product. So down here, this is like what would not happen. This would be an incorrect orientation. So they're colliding, but if the O is going to be between the two ends, that's not gonna make the product, and those two reactant molecules are just going to bounce apart. Okay. Any questions about that? Now, before, like, there's a moment when the reactants are becoming the product. That moment, that structure that happens when the reactants are becoming the product is called the activated complex. So think of a complex, like when I think of a complex, think of a mall. Complex is a bunch of different things kind of together. So here, this complex is of two reactant molecules, and they are activated, meaning they're activated because they're colliding with the right amount of energy in the right orientation. And step one, again, they've collided. Okay? So if they don't collide with the right amount of energy, or again, in the right orientation, they will then go back into reactants. Okay? This is really a foundational slide to understand. If you don't understand this slide, you're really not you might be able to answer some of the problems with the energy diagrams, but you're not really going to understand what's happening. So make sure this makes sense to you. We have questions on it? No. I'm not going to ask you what is the right orientation. No, it's just understanding that idea. Just the idea that there is a right orientation. Okay? Only if you're like a chemist would you have to like try and figure that out or something. Okay, so looking at our energy diagram and kind of basically what we're doing on this slide is we're taking the three parts of the collision theory we just went over on the last slide, and we're going to put it onto the energy diagram and interpret it. So here's my two reactant molecules, my two nitrogen dioxide molecules, and I want you to think of them as like a boulder. Like if I am trying to push a boulder over a hill to break the boulder, I first need to put in energy to get that boulder over the hill. Right? Like if any like by definition, to roll something down a hill, you have to get on top of the hill. Right? If you ever gone sledding, it's a lot of fun going down the hill, but what's not so fun? Going back up, right? So appreciate that you always have to put in what we call activation energy. Activation energy is the amount of energy you have to put in to get this boulder over the hill. Or in molecule speak, the activation energy is the amount of energy you need to have in order to make these molecules collide. First part of collision theory, molecules have to run into each other. Think of like temperature. If you raise the temperature, we said a higher temperature means what? When you're talking about like molecules. What are the molecules doing at a higher temperature? They're moving faster. How do you get a higher temperature? What happens to your energy bill if you just keep running the heat? It goes up, right? You add energy, molecules move faster. They move faster, they can get over the activation energy. Okay? All right. Now then, at the very top of this hill, this represents high potential energy. There's a lot of potential energy here. A lot of energy to do something. If you're a boulder at the top of the hill, because of the fact that this boulder can go down and gravity can pull it down, there's a lot of energy to do stuff there. In molecule speak, this is what we call the activated complex. When you have collided these two molecules in the right orientation, they then have a ton of potential energy there. Okay? Highly unstable would be another way to think of it. Equals unstable. And because they are unstable, they will then rearrange to form your new product. And by rearrange, I really mean like they're forming a chemical bond. There's going to be a sharing of those valence electrons between these two molecules to form that new product. Okay? And this is like in the downhill portion of the graph, where this is favorable energy-wise. So, favorable process. This is favorable, meaning like it doesn't require energy to make that happen. Energy is going to be given off when you're going down like that. So favorable equals release energy. So compare that to up here, we're going uphill. This is unfavorable. So if something is unfavorable, it requires energy. Hence the activation. You have to put it in to get these two molecules up to that top of the hill. Okay? It's super important you understand this. Otherwise, the rest of it's just kind of, it's not going to make sense to you. So questions about this? Okay. Keeping it moving. Looking at our energy diagrams. So on that last slide, I said, really last class, I talked about how we're measuring energy on the y-axis when you're looking at an energy diagram. Where if you're looking at an exothermic reaction, like what we saw in the warm-up, exothermic reaction, your products are at a lower energy level than your reactants. You would see this as enthalpy. That's another way you'll see these y-axes. You'll see that measured in enthalpy. Enthalpy, potential energy, they're not technically the same thing, but they're related to the same idea. For our purposes, you could think of them as essentially being the same thing. Here, if the products end at a lower potential energy or enthalpy than the reactants, that is why we said it is a negative delta H. Energy is going to be given off. Energy is released because you have decreased. So this right here, this is your delta what? Delta H, which here equals negative because products are lower than the reactants. Okay. Up here, this top portion right here, this is your, this arrow right there, that's your activation energy. So that's the energy you have to put in to get those reactants to this portion. What's top of the hill? What do we call that? Any thoughts from the last slide? No? Yeah. Activated complex. Good. Activated complex. All right. Now let's compare that to an endothermic reaction. Endothermic, you have to put energy in dough, right? So the products are going to end at a higher energy level than the reactants. We would say energy is absorbed. Or another way of saying that, if we're talking about enthalpy, is it is a positive enthalpy. Okay? And think of it like potential energy. There's more energy stored in these products. Think of it like you're trying to charge your phone. You could get more energy out of these products, if you're to charge your phone or whatever you want to do with that energy, compared to the reactants. Whereas this is the opposite. There's less energy available in these products to do work with, to do things with. Okay, so this is kind of getting into a lot of the questions you'll see is really interpreting this diagram here. There's really a lot of, again, like where a lot of test questions come from. So x-axis is time. Sometimes you'll see that as like the rate, or not rate, the progress of the reaction. Y-axis here is potential energy. Again, it's also can be expressed as enthalpy. Spelling's a tough day for spelling for me. See, that's H. So here, and they typically measure it in joules or kilojoules. So the K means kilojoules. It means 1,000. So it's like 45,000 joules as opposed to just 45 kilojoules. Anyways, reactants are at 45 kJ. Products are at 10 kJ. So what they would want to know is, all right, what is my delta H? Like number-wise, what would the delta H equal here for this reaction? -35, yeah. -35, though. I don't know if you said negative. -35. It's negative because the products end at a lower spot than the reactants. It's 35 because the reactants are at 45, products are at 10, so 45, when you're doing like this calculation, what you're actually doing is you do final minus initial. So the final reactants were 10 kilojoules for your products. your reactants, your initial was 45 kilojoules. So 10 minus 45 is negative 35 kilojoules. I imagine for most of you, you could probably do that in your head at this point in your science career. Now then, other things to note on this this graph. The activation energy. So there's an abbreviation for that just because it's a pretty long thing to write out. EA, A for activation, E for energy. So what would my activation energy equal here for this reaction? How much energy do you have to put in? Do you have to invest? Think of investment. You got to spend money to make money. That's what's going on. If I want to make some money, I want to release some energy, I got to first invest some amount of activation energy. How much energy do we have to invest into this reaction? 58. Yeah. How he got that is the top of the hill, which is the activated complex, is at 103. Bottom of the hill is 45. So the difference between those numbers, if you do 103 minus 45, that would be 58 kilojoules. Okay. So compared to stoichiometry, this math is not crazy complicated. You just have to be able to interpret these graphs here. Other questions could be, what's the energy level of the activated complex? What does that equal? What's the potential energy of the activated complex? 103. Now, another way that they'll say that is, what is the heat of the activated complex, or the H of the activated complex? That'd be the same thing as asking, what is the energy of the activated complex? Or what is the heat of the products? That would be 10 right here. The H of the products, the enthalpy. H also stands for enthalpy. There's kind of some more or less synonyms you'll see with these. But notice how this is labeled for you. Like on a test, like I could like not label these H reactants, H products, and have you label it for me. Or like on the worksheet that you have. Okay, keeping it moving. Here's the last slide, right? Yeah. So last slide, and this is similar to what you're going to see on your worksheet, is interpreting one of these diagrams. So first question, what is the activation energy for the forward reaction? Now that's interesting. What do they mean by forward reaction? Any thoughts on that? As opposed to the reverse reaction. I haven't talked about that so far. What would that mean? Victor?
I think the forward reaction would be the AB plus the ABC.
Yeah, right. So if I were to write this out in reaction speak, my reactants are AB plus C. And my products are A plus B, C. So the forward reaction is just your typical reaction. You go here, you go there. But in chemistry, this reaction, some reactions, a lot of them, can do a reverse. Meaning these products can actually go back the other way in the reverse to remake the reactants. Okay? So anyways, question 11 then, what would be the activation energy of the forward reaction? What do we think? Sure? What is it?
60. Oh wait, for the forward reaction, I'm 80.
Okay, so it would not be 80. Even though you're right, like if I asked what's the potential energy of the activated complex, ABC, that would be 80. So then what would, Nora? 20, good. It's the difference between where you start and where you end. Okay? Okay, so this would be 20 kilojoules. All right, then what about the reverse reaction? Sure.
60.
Yeah, good. 60. Because if you're doing the reverse reaction, again, it's starting with A plus B, C. This would be the reverse reaction. And the reverse reaction, your products are now your reactants, and your reactants are your products. So now I'm going this way. Now I got to climb this giant hill. So I'm starting here at 20, and I need to get to 60. So I would need to put in 40 kilojoules of energy if I'm going in reverse. Okay. All right, now then, what is the delta H, or the change in enthalpy for the forward reaction? So you're going this way. What do we think? Haley? Oh, my fault. Yeah, you're right. Good call. Good catch. We stop up here. Yeah, thank you. I don't know what I'm doing. Yeah, we're going from 20 up here to the top of the hill, 80. So it's 60. So not up to there. You got to go all the way to the top of the hill. See that? You got to push that boulder all the way up here. All right, 13 then. So what is the delta H of the forward reaction? So forward reaction is just going left to right. Negative 40. Yeah, good. Negative 40 kilojoules. So how Nora found that is you're starting here at 60, and then you're going down to 20. So if I were to write it out kind of formally, delta H is final minus initial. So your final is 20 kilojoules, and your initial was 60 kilojoules. So 20 minus 60 is negative 40 kilojoules. But again, if you probably could do a lot of these just by reading the graph and kind of do it in your head. All right, so negative 40 kilojoules. Now this is interesting. What is the delta H for the reverse reaction? You want? What was that? Positive 40. Good, yeah. Because now you're going reverse. Now you're starting here. So notice this. This is actually really important. Delta H for a reaction, whether you're going forward or reverse, delta H value is same. Like when I say value, like the actual number, I'll say absolute value. That'd be the mathy way of putting it. Remember, absolute value, you don't care about the sign, you just care about the actual distance from zero. Our distance from zero is always 40, so delta H will always equal 40 something. It's always that difference, but whether you're going this way in the reverse or you're going this way, it's going to be about the sign. So usually you'll see people emphasize the positive if it's positive 40, just to again emphasize that idea that like you're changing the sign. So delta H for a reaction is always the same number, you just change the sign depending if you're going forward or reverse. All right, last question, 15. Is the forward reaction exothermic or endothermic? What do you think? So this is actually just like the warm-up question now. Peter? Yeah? Exothermic, good. Exothermic. And he knew that because the products are lower than the reactants. Reactants are higher. Okay? Then what about if you're doing the reverse reaction? So if I'm going from here to there, what would be the how would you describe the reverse reaction? Endothermic, good. Be the opposite. So that's really about it. You know, I think we've done harder things this year, but you just gotta know like what they mean when they're talking about these different parts of it. Some other things they could ask. What if they asked H of reactants? What is the H of the reactants? Make sure you there'll be a question like this: H of the reactants. What is the enthalpy of the reactants, or the energy of the reactants? It's just 60, yeah. It sounds a lot more intimidating. That it's just, these are the reactants, right? It's just 60. Now, technically, I would need to say the forward reaction, because what if I said H reactants of the reverse reaction? Then what would it be? It'd be 20, yeah, it'd be this. So H of products, that would be 20 kilojoules. H of the activated complex, we'll say AC, that would be 80. That's the very top there. Okay, so that about does it. So you got a worksheet there, some extra practice problems. Going around the room if you got questions.